We left off was we were introducing vector loops and applying them to mechanisms, all kinds of mechanisms, and what we showed initially was the applied to the crank slider. Right, so what we did is we replaced each of the link with a vector, and each with a vector with the magnitude and angle, and we drew a loop. And this way we went clockwise. So, and we came to the rule that, like, if we're going in direction with the arrow, it's going to be a positive, and that's positive. But then we went backwards against the arrow, and we went negative. And then we could draw and break this thing into the x and y right here, components of this thing right here. So, and using the angles as being from horizontal on the right side and going counterclockwise right there. So as part of that, so in the x direction, we would find that by taking the magnitude. We call this the magnitude of this length A. The magnitude of this length is B right here. So we're just using the cosine of those angles here. And in this case, this one's completely horizontal, so we didn't need to do that with the angle. And then we did in the y direction. And solving these equations will enable us to get the position. And I made a comparison to what is done right here, at least in respect to this guy right here. So, moving on. We also want to I also want to show how this vector loop is applied to things that we very common mechanisms, the common basic mechanism types here. So if we're going to do this for a 4-bar right here, using the same conventions, right? So we have that A, B, C, and D for these lengths, and theta 2, theta 3, theta 4, and theta 1 is going to be treated 0 quite often. So if we're just going through here and going through the loop, and we notice that we decided that we're going to take the this branch and make its base from here and here, but we decided to, and we also for this one for the ground we're going to take it from there. But for this one we decided to come up this way. So you'll notice that we're going to go forward through the arrows and then negative through the arrows right here. So these end up looking like R2 plus R3 minus R4 minus R1 equal to 0. Right? And then for now here's the offset slider crank. So now we have an additional vector that we didn't have in the other one right in there. So we're going to say, and once again we're going to come in here. Sometimes people will include this as a vector, right? That can be done as part of the solution if they want to, but we won't, at least not now. So we're going to go R2. You notice that they decided to make this one come up this way. I guess it was easier to pick this angle as opposed to making it this angle right in there. But this is just a convention that they're using, right? So there we get the R3 right in there, and we're coming backwards through the R4, and then we're coming backwards through the R1. We could do the same thing for the inverted slider crank right here. Sometimes I think of him as more of a quick return mechanism right here, but this is another way, is the inverted one, where we see that this little thing represents that this remains perpendicular all the time to this. We also add in, sometimes we'll add in this gamma as part of the thing. That gamma will often be 90 degrees, right? As it's shown right here, that looks like it's 90 degrees, but it didn't have to be, right? It could be, but this is like a fixed angle. That's part of there, but just be aware this is a common problem if you look into the back, the back of each chapter on our good friend Bob Norton. He has a lot of problems that are based either it'd be a 4-bar a offset slider crank or this inverted slider crank. That's like the number three, the three things he likes to have as these basic mechanism. So, and then once again, you'll see that we are coming down and coming through and going in negative there. And you also see that here's the arrowhead for this R4. So going through and clockwise, we have positive for R2, and we're going to have negative for all the other ones because that's the direction that we've chosen. And it's all about the angle, really, in making that decision. So far, this is not a difficult topic, right? But now, as we start to get into the nitty-gritty, as we try to solve these problems, is where we have some issues. So here is not too bad. It's actually pretty easy. This is like the easiest one to do. This is the crank slider, right? So the crank slider, we wrote out this vector loop equation already, and then we can break it down into the x components and the y components of this, right? And you can convince yourself that these are all true right here. Noticeably, they made the decision that this is going to be equal to 90 degrees right there. So we could see that if in the x direction, even if you just like lay out what these are, right? That this one just has this amount of x, and this one has this length right here onto the thing. Okay, wait, no, this one has this length right into here, right? And then this one has this length, this D right here. And you can see that, like, yes, this one, and by the way, you have to be careful of this angle is right over here. So that's going to tend to give us like a negative, like this is going to be greater than 90 degrees. So this actually ends up being a negative number, even though there's negative right there. So just be aware of that. But that we're going to have a positive, we have this length and that length together is going to equal this, so it's going to equal 0. Same thing here. But you know, this also, you're going to be careful here. This I believe that's going to give us, I think it's actually harder to do that with an angle that's greater than 90 in the sine. Is that true? No, I think it's greater than 180. It might give you might get messed up. No, I think you're going to be fine, right? It's going the other direction that you get mixed up. If you do the inverse sine or something, yeah, okay. So like if you had like 210 and took a sine, yeah, you're going to get a negative right there. Okay. So anyway, yeah, you were going to get the negative right in here for the thing. So you would have this length right here for the A, and then this length for the B, but then you would have like this length for the C, and so that they would cancel out to 0. So in a crank slider, right, what we know is we have theta 2 as an input right here, right? And then all these other things are the same. The lengths are the same, A, B, and C. Theta 1 is going to be the ground link is there, is set. Theta 4, like we said, is 90. So the variables, the unknowns from these two equations are going to be this length D and theta 3. And that just makes sense, right? You're cranking this thing in here, and it's going to change where the position of this is going to go back and forth and back and forth. So D is going to be one of the outputs, and this angle theta 3. So we can solve these pretty easily for what that theta 3 is going to be. And that subscript 1 is that this thing has an alternate solution, right? And that alternate solution, I believe, is going to be like laying down over here, over to the side. Right there. Given these parameters, you could have this configuration, and that would satisfy all of them. And then once you have that theta 3 in there, it's easy enough just to solve this equation right here to be able to get what that distance is. And that distance is the thing we're going to probably care about the most, right? And so here you go. This is like the one of the big troubles that we have right here is that theta 3 it can be multi-valued right here, right? When you take the inverse sine of something, you don't necessarily know whether it's positive or negative, right? Based on the thing. So there's two possible sine angles that can exist for an inverse sine, And so the other one that's possible is adding 180 degrees to it. So now we have two configurations. We have an open configuration and a crossed configuration that are possible. This is something we're going to keep seeing in this position analysis right here. So for the crank slider position analysis, I have an example. And I'm looking at my time, trying to figure out how I'm going to squeeze all of this into one thing and how I maybe should have recorded my videos. So anyway, here are some parameters we're given for a something that has a 40 millimeter crank, 120 millimeter connecting rod. It's going to have an offset C right here. So the offset is a negative 20. So that means that the, as the one that we just showed previously was offset so that the line that it ran above was above the center line, right? Here would be the normal center line for something. Here's offset this way. We decided that C was going to be a negative value. So if we want to find for all possible values of theta 3 and D, if we have an input of 60 degrees right in there. So we use the equations from this, and we take the inverse sine of A sine of theta 2 minus C divided by B, right? So plug in some numbers right here. And we get 40 sine of 60 minus 20 divided by 120. And so that theta 3, 1 is just going to be 27.09. So when we want to find the diameter, or not the diameter, but the distance, and this is going to be the one that's in the open position, we take A times the cosine of theta 2 and minus B times the cosine of theta 3. We find that we get 40. Oh, and by the way, I just misstated. It's not necessarily going to be the crossed. One of these is going to be the crossed, and one of them is going to be the open, right? One of the two possible thetas, theta 3s that we're going to have as part of this. So we'll just plug these in, and we're going to see what result we get. We get a negative 86.84 millimeters. So this is, therefore, this is the crossed configuration. That's this one right here, right? Coming backwards that way. So now what we say is, well, that means that the other one, the alternate solution, was going to be negative A sine right here. Okay, so remember I said that like we had either this solution or we have this solution here where we're going to make this a negative value right here and then add pi to it, right? Or 180 degrees, I should say. So so we have sine theta 2 C minus C divided by B, and then we add pi. So if we put all of those things in there, let's just say that we did, we get 152.9 degrees. And if we plug in D, 40 times the cosine of 60 minus my 120 times the cosine of 152.9, it's going to make a negative number, so it's going to take care of that right there. We get 126.8 millimeters. And now I show it this for an Excel spreadsheet. I find that this makes it nice to make a nice tool that I can use and try to analyze for other things. So let me see, what is my, I have 14 minutes. Let me pause that just for a second and open up my Excel. Here is where I have built an Excel spreadsheet to have like for my own benefit, but also I think I have made assignments before that use this right here. So this is example problem 4.2, and I pasted in the information. I put in pasted in equations into it, and then I wrote down my givens with the variables. I put the inputs as yellows, and so what I have over here, here's my taking the inverse sine of if maybe we could maybe I can move this guy right here so we can make a comparison of what I have. Let's see here. See how clever this is of a thing. All right, so I took the arc sine of my, okay, so here's, let's see, so I'll make this half the page right here, and then here's half the page. There you go. So right here you could see that there's A right there. And I can also define these, by the way. I always forget that I could do that. I could define each cell and give it a variable name, but I just went ahead and called up the cell instead. So C14 times the sine of this angle, and I made the radians over to the side next to the angle. I could have just put it as part of the equation in here, and then subtracted out C, and you see that it's a negative right in there, and then divided it by that B right there, just like I've done over here. And you can see what I get is this in radians, and I can see that I have this angle right in here. And then I did the same thing for here, but you could see as I took negative right in there, and then I added pi to it, and then you could see here is the 152.9 that I get. And then I can also solve for my D right there. I'm solving right here for the D as part of this, and I say that I have the cosine of that angle right here, the input angle, times this, and subtracting this B times the cosine of this angle I just got right there, and you can see that I get the negative 86.84. And then I do the same thing for this, but I'm doing it for this other angle right in here, the alternative theta 3. And so I left with that 126. So if I want to see what these look like, I plot them out this way right here, where I take for each of these points, and then I repeat the second point right here. So here's the O2, the A, B, O4, and C. They're labeled just like this is right there, right? So I take and I call up what these right here are all just 0. I know that they're 0, so I'm using that as the baseline. But I call up this A and this theta 1 right there to get that x coordinate, get this y coordinate, the same thing right there. And so these two are based on that theta 3, 1, right? And I go to the A location right here, and I go to the B location. And when I go to the B location, I also go to the O4. So in mine, I went to here. Let's see. Where did I come from? Right in there. Okay, yeah. Okay, so yeah, because I know I'm calling, I think I'm calling this the O4. Location right there. Yeah, okay. So I have B, and here's where my O4 is going to be, down here on the bottom. Yeah. So anyway, you could see this grouping right there. I just plotted this column versus this column, or actually this column versus this column, and it gives me this configuration. And I do the same thing for over here. So now you can see, so now I made a tool, right? So I could say, here's what happens. Let's see, I could change this to 45 degrees. Didn't really make much of a difference there, did it? 75 degrees right there, right? So you can kind of see how this thing is stretching out. And you got to be careful with the ranges of this and the proportions. You want to try to make these, when you stretch this thing out, try to make these into squares so that they are proportional. So anyway, this is a tool, and I make this for each of the ones. So my video got kind of long. Hopefully I can keep the class down. This is like 20 minutes. Let me go to the next topic in a new video.